Australia. And down the bottom we have Dr. Miles Benton. He is our bioinformatician with technical expertise in lots of things with regards to genome informatics, including NGS analysis. Miles and Robert, we've got maybe 40 odd people here today. It was maybe a bit bigger than I was expecting.
Oh, well.
And these are all researchers and students from Saigon. University Hospital in Ho City. They're all here today because they're interested in genomic medicine generally, and a bit more specifically interested in bioinformatics, the role bioinformatics plays in this field of genome medicine, and there are a few people doing NGS-based research projects. What I was hoping Robert and Miles could show was an overview of our NGS diagnostics pipeline, and work that we do, our program at QT in Australia. And so I think Robert is going to start with a bit of an overview of the diagnostics pipeline. And I think Miles is going to do a bit of a demonstration perhaps of one of the tools he's recently built to help process the DNA sequence information. So just your information, Robert and Miles. People here don't necessarily have a great deal of expertise in either NGS or bioinformatics. So they want to learn as much as they can from you guys. So maybe Robert, do you want to start?
Yeah, okay, I will kick off.
Just before Robert does that, I'll point out that Robert is in Queensland, Miles is in Wellington, New Zealand. As I mentioned earlier in my talk, you don't need to all necessarily be based in the same facility to do bioinformatics. So Miles and I work very closely, but he lives in Wellington and I live in Newcastle. We both work for QT.
Okay, no worries. Can everybody see the presentation?
Yes.
Okay. So this is a description of how we do our collate work with the diagnostic of neurological disorders that we do. So I just give this overview of our pipeline, and Miles will be giving the technical stuff afterwards. So we're an accredited diagnostic, and our work has grown from a research interest in migraine and early migraine syndromes. So the diseases that we work with are real imaging migraine, episodic ataxia type 2, spinocerebellar ataxia type 6, and this very large disease here, cerebral autosomal dominant arteriopathy with subcortical infarct and leukoencephalopathy, which is just cancer, and we're also working on epilepsy. So in 2012, we started our next generation work, and we did this by developing a next generation sequencing panel that just covered the genes in disorders specifically. And that panel, which was 5 genes, was really successful. We ended up being able to diagnose 4 times as many patients as we were able to do before. despite that, we're still only getting somewhere between 20 and 28% of patients, depending on disease. So there are clearly mutations in some of these individuals that we're missing. And so that's where we moved on to now this exome-based approach that we're taking up. Do let me know, by the way, if I'm going too fast and people can't understand. So this is just the genes that are involved in our panel, -1, which is complete coverage. And this gives you an idea about how many exons are involved. So the blue boxes in white that you can see here, these are the exons that we used to do when we do this by direct stack sequencing. These are the exons where most mutations occur. But we're still only getting about 5% of patients with those. The actual design for the next generation sequencing panel covers the entirety of these genes. The little grey boxes here are the exons where the coverage isn't perfect. There's small pieces missing. We get 91% of the target area, and as the technologies improve and the read length of our next generation sequencing system has increased, a lot of these gaps are now closing, and we get more or less coverage. So that was fine to start with, but as I said, we're still only getting somewhere between 20 and 30% of the patients. So we started this exome sequencing. And using our proton sequencer, we can extend our reach to other genes. We're in the final stages of getting this method accredited in Australia. We're just now waiting on a few small changes to our facility to allow us to go ahead with it. But the use of whole exome sequencing, while it's a wonderful thing and improves our chances of finding mutations, drastically increases the difficulty of analysis, and that's what we'll be talking about here. So what you can see here is our general approach. So we'll get a request for genetic testing, and if it's a no mutation or a simple disorder where the mutation can only occur in a very limited space, we'll go straight to SAM sequencing for that, because it's cheaper and easier to do it when we know what's going on. And you might get a complete diagnosis, or we'll get nothing and then we know a conclusive result. And a proportion of those people won't have the disorder at all. And in a simple situation, that's fine. Where things are more complex, where we don't know where the mutation is going to be, we have to go up to this side, where we have our next generation sequencing panel, or exome sequencing, or in extreme cases, we might have to go to genome sequencing. Now, we have the same results here, but the problem is that the complexity of this analysis increases enormously, going from the NGS panel all the way up to genome sequencing potentially. So this is an example from our next generation sequencing panel. We generally get about 60 variants per individual in the 5 genes. So as you can see here, 57 in this particular person with a few variants here. And most of these variants have very high minor frequencies, 13%, 46, 23. These are nothing to worry about. We can skim over these fairly quickly. So that makes working this simple by just doing it by name. But for our next generation sequencing, we're getting 35,000 variants per person on average. This makes it really hard for you to find mutations, and as you'll notice, the reference value frequency and alternative frequencies are 0. These are all rare variants we're looking at here, just in this capture alone. So trying to go through all this is really, really difficult. That's where we came up with the pipeline. So we've decided to use a tier-based analysis method, which mimics the process of intravenous testing, which used to be the standard in hospitals, where you would start with the most likely to be mutated, and then you would move on to the exons that were the next most likely, and the next most likely, and so on until we reached, hopefully, the end of the testing and found what the problem was. Each tier on this system is made up of a gene list that represents the set that is started with more likely to be involved in the disease and less as we go out. And it's similar in principle to a recently published method, but we didn't come up with this independently. So this is a CPIPE, which is another method that follows a similar kind of process. And these are our tiers here. So we have this targeted model that moves out and out as we go, and this overlapping tier, which I'll discuss in a moment. So in tier 0 here, we have the genes that are in our next generation sequencing panel already, the 5 genes we know that cause our disorders. Now, we have this in here for 2 reasons. The first is that if there's already been a test before using the panel, doing it again and looking at the data allows us to compare the 2 results and see that the quality of our work is good. So we get those variants that we have again. If no testing has been performed in this individual for our panel, it gets us to look at it first, because those are the most likely to be. tier 1 are genes that are relatives of the genes that you just have, so they're in the same gene families. Or there are other genes that are known to cause similar disorders, because there's a lot of symptom overlap in some of the disorders that we do. Lots of different kinds of migraine, lots of different epilepsies, and the different kinds of ataxia as well. Tier 2 are genes that are involved in metabolic pathways that are consistent with migraine with these same effects. So things that are nervous system, ion channels, hormone regulators, and things like that. The third tier is all genes that are simply not in lower tier. And the fourth tier are polymorphisms from all of these tiers. Those are variants that have minor low frequencies above 10%. We separate them out, put them in their own tier. Those are generally more interesting from a research perspective rather than from a disease diagnostic perspective. It's unlikely they're going to cause any problems. Within each tier, we also have a number of sub-tiers, and these are designed to help speed and aid the way we do this analysis. The first of these tiers are what we call mutations and variants. And these are things that change the amino acid structure of the protein or otherwise affected in ways. And these are ranked by the in silico vectors that determine the severity. This is based on the conservation of the sequence in the region, the magnitude of the amino acid change, or any splice variation that could be happening. These are the top 10 this first tier. The second tier are what we call mutations. These are amino acid changing variants that have no known SNP number. So these are variants that have not been seen before or are so rare that nobody has annotated them yet. Third tier are variants, and these are things that are not amino acid changing but don't have a SNP number, or they're amino acid changing or non-amino acid changing, and then minor low frequencies are considered to be less than 1%. So these are very rare variants that may be affecting disease. And now in the fourth tier, we have rare polymorphisms. These are variants that lead up to that fourth major tier, all the variants that are between 1% and 10% in a minor low frequency. So our analysis system is modular, and the processes going on for each tier are identical as we go, and Miles will show you more about how that actually works in a minute. The genes can be updated quickly using GitHub storage or master file locations, and these tiers are not set into the program. They're a list that we can update and curate as we go. So as new information comes to light from research, we can move genes down a tier if we think they need to be, or maybe move them up again if we think they're not as likely to cause disease. We can also add more tiers because this is a modular system. And as an example of that, for epilepsy, we've developed an alternative tier system that splits up the genes that we're analyzing into different forms of epilepsy. And so when a clinician asks us to have a look at, say, Dravet syndrome versus generalized epilepsy, we can go straight to the category of genes that cause the thing that the clinician wants to know about and look there first, and then we can start moving out as necessary. So what happens in the overall process is that the data output from a proton machine undergoes basic analysis on the proton server to produce the VCF files and the various underlying structures that we need. The data is then moved to a custom analysis server. A staff member logs onto the server, executes the analysis, and the staff member can choose which tiers and things that we want to use as part of that process. The analysis is completed and the report is automatically generated in about 30 minutes, and I believe that Miles actually has that time reduced now. Yes, about 10 minutes, isn't it now? It's about 10 minutes now.
Depending on the size of the return, and the number of minutes, the quickest it's done is about 10, and the longest it takes for the largest experiment we have is about 20 minutes.
So that's good. So it's nice and fast, which is always a bonus. And the report is complete, along with the report that is generated, a complete variance list and additional files are automatically archived by the system. And that's useful for us from a diagnostic perspective because we need to have version control and continue to know when a thing is analyzed, how it is analyzed, and keep records of this thing. If patients come back to us for information, particularly if there's new data that arrives from research or other sources that might mean we need to recheck our analysis in the future. And all of these processes and analysis parameters are logged for traceability, so we know how it was analyzed, using what methods in the genome, using what versions of what programs and all that sort of thing, so that we can go back if there's been any problems and diagnose where that problem came This is just an example of what the test report will put out. So we have information on the patient, the run ID, the run test, so this will have a name in the final version, so it will be, for example, a migraine panel or an epilepsy panel or something like that. It will tell us what alignment was performed against one version of the genome, the annotation pipeline that was used, the various versions and things like this, and then it will start giving us information about quality. So anticoms with their read percentages, what overall quality we have out of an individual. We will see the total number of variants, the maximum amount of coverage, the minimum amount of coverage, the mean coverage, and so on. This gives us an idea about overall quality, and from a diagnostic perspective, lets us know if this is data that we need to repeat because the overall quality is not good. It will then give us summary statistics about the samples that we've got, and then it will actually start producing the tables. So we have here a list of the most damaging variants of this individual, which belong to these genes that are involved. So the SCN1B is relative to the SCN1A gene, is our primary panel. CACNA1S, which is again a relative of the CACNA1A gene that we look at. These are amino acid changing variants, there are information about the prediction that the in silico software has said about them. In this case, SIP and polyphase have both called this variant deleterious, and mutation texture is indicated as possibly damaging. So we have two damaging, one possibly damaging. It gives us an idea of the severity. We get coverage statistics here, which can let us know whether we think it's a true variant or not, whether there's something else going on. And it gives us an idea about what the alternative and reference frequencies are for the variant. And these ones are actually relatively common, but because this is considered damaging, it appears under this damaging tier. And it's possible for the few rare SNPs that do have fairly high number of frequencies to be damaging. An example of this with different gene set is the gene ApoE, which is somewhat common and still causes disease. And we move down the various tiers and start to see these more unusual ones. So this one, for example, was pulled out, ATXN2, which is also in this list. This one has no SNP number, as you can see here. It's amino acid changing, and we get 2 scores of deleterious, and we get 1 score of benign. So this is one that merits further investigation in this individual. At the very end, we also have a Luminosity mutation assessor, which is a very useful program which can show us the 3D structure of proteins, where the mutation is in the 3D structure, and this is useful for us to be able to look at the mutation and see whether it's in an important functional part of the protein, which can be useful when the silico predictors give us ambiguous information as to whether we think it's a problem or not. So overall, the analysis and report structure has sped up our analysis tremendously, trying to do 35,000 variants by hand. It's a process that will take weeks and weeks. It's mostly automated. We now have a website interface, which Mars will be able to show you, which adds additional functionality as needed. And that modularity to the system makes it flexible and able to adapt with us. So as the information comes to light, as we achieve new needs and new things we need to do, we can add to the system and make it work effectively for us. That would be the end of my part. I don't know whether we have a question time or whether we're moving into Mars's talk. I'll talk straight up.